Okay, so
Okay.
welcome everybody to the fourth and last lecture in this lecture series by David Shee. And please, David, go ahead.
Great. Okay, so the plan for today is I'm going to finish talking about GANs. I'm going to show you some demos of how GANs work, talk about some of their problems, and also talk about some of their physics applications. So, and then after that, I want to squeeze in, a very brief overview of anomaly detection and searches for new physics using machine learning. All right, so why don't we get started? So last time yesterday we finished by talking about why GANs work. Okay, so first we defined what the GAN is. It's this adversarial setup where you actually have two neural networks that are competing against each other, trying to defeat each other. And what that means mathematically is they're trying to achieve a saddle point optimization, or a saddle point extremum of the loss. And what the loss is basically the negative. Well, it's just conventional. The sign, of course, is a matter of convention. It's conventional to take the loss to be the opposite or negative of a classifier loss. So the opposite, so the actual binary cross entropy, not the negative binary cross entropy, in other words. And it's between the real images drawn from the data and the generated images drawn from a latent space with some simple probability distribution that you specify beforehand, like a uniform distribution. Okay, and so typically one trains these two networks. There's different approaches, I guess. I've never done a GAN for research, so all I know is based on these demos and things that I coded up. And so what I've seen in these simple demos is you train the generator and the discriminator one after the other. Okay, so I've also seen it said in the literature or on the web that there are approaches where we try to train them concurrently. But yeah, that can be tricky, I guess. So typically people just imagine alternating the training between the generator and the discriminator, and then how long you train each one for, what their learning rates are. These are all hyperparameters, and so you can think of one drawback of GANs is that having two neural networks that are finely tuned against each other leads to a more delicate hyperparameter selection procedure, right? So it's not like these classifiers that I showed you earlier, where you just basically write down anything, and with the Atom optimizer that picks a learning rate for you, you don't have to really think about it. With GANs, I think in general you do have to think about it, or you have to play around with these things. So it's an extra headache. But for a good payoff, you get very nice images and things. Okay, and the last thing we talked about yesterday was the optimality guarantee of GANs. So if things are working theoretically, the GAN should fit the GANs can in principle achieve their objective, which is to generate fake images or fake data drawn from the same distribution as the real data, right? So we went through this proof here. We took the loss, we maximized it with respect to the discriminator, plugged it back in, minimized it with respect to the generator, and we saw that it gives us this JSD, Jensen-Shannon distance, which is minimized when exactly if and only if the generated probability is the same as the data probability. Okay, so that's where we left off last time. And anybody have any questions about that? As I'm going to pull up a demo now.
How does the generating part actually work? The detection part can presumably use one of these convolutional network thingies.
Yeah.
But how do you go from order 100 random input parameters to order million pixels?
Oh, okay, good.
Other direction, that is, with the generating.
That's a great question. So maybe I can. So the So the discriminator and generator are neural networks. And just like any neural network, you have the choice of what architecture to use. So for example, just an example, D could be the discriminator. It's a classifier, so it could be one of the simple DNN classifiers we've considered previously. And then, yeah, your question is, what is the generator? Well, again, there's a choice there, but the generator for G, it should map Z from the latent space to typically a much bigger space, X, right? In the data, right? So maybe X is like an image like that, right? So how do you map this to that? Well, lots of options. You can do a CNN type thing. There are ways to do CNN convolutions in reverse. It's called upsampling. So you could do that. You could also just do a fully connected neural network. So just make the hidden layers bigger and bigger until they reach the data size. So those are some typical options. With the demo, I'm going to show you. I forget exactly what I chose to do, but I think I just did a fully connected neural network. But yeah, does that answer the question?
Yeah, thanks.
Okay. Oh, and the last thing I should say is that Z is sampled from some specified probability distribution to begin with, like the uniform distribution, for which there's a quick numerical pseudo random number generator way of doing it in any of the standard Python packages. Okay, so let me show you a demo now. So this is something you can link. There's a link to this on the website for the lecture series, and all I did is I just sort of basically mostly cut and paste from this link. Okay, so you can also find this the same thing done here, and with many more explanations. Okay, so I didn't come up with this on my own. All right, so what are we going to do in this demo? We're going to train a GAN, and I should say that what I've described to you so far is basically the content of the original GAN paper, the 2014 paper by Goodfellow and Company, and so this is by no means state of the art anymore, and it's just the simplest thing that we're using to illustrate the idea. Okay, so this vanilla GAN is not going to perform especially well. Okay, but anyway, so what we're going to do is we're going to generate the handwritten digits. So there's a database of handwritten digits 0 through 9 called MNIST, and you can very easily download that. And there's 80,000 images. Okay, we're going to train the GAN on 60,000. I don't know why we need to test that actually, but yeah. So let's see, can I visualize one of these images real quick? Where did it go? Oh, what did I just do? Sorry. Yeah, so let me see if I can visualize one of these images real quick. Okay, that did not load. There you go. So the first image in this MNIST database is a 5. All right. And so that's the idea. These are 28 by 28 black and white, grayscale images of handwritten digits. Okay. So these are famous sort of classic. This is a classic data set used to test out many deep learning algorithms. The original CNNs were developed in order to classify MNIST digits as their sort of trial task, and many deep learning algorithms are demonstrated on the MNIST data set. Okay. So it's kind of like a mouse model for deep learning. All right, so here we're going to define the GAN. Okay, so just stop me if you have any questions. Oh, I was wrong. So the GAN that we're doing here is using convolutional layers. Okay, so the discriminator is a CNN classifier with two convolutional hidden layers with 64 filters each. Some extra bells and whistles here that we don't need to concern ourselves with. So it's a very simple, small discriminator. It's trained with some learning rate that's different than the default, which is part of the fine tuning that you have to do to get the GAN to work. And okay, so that's the discriminator. Okay, you can see what it looks like there. It has 40,000 parameters to it. Okay. So here we demonstrate, training the discriminator to tell real versus generated samples. So we create something that randomly selects real images from the MNIST data set. And here we generate random samples, but this is with a generator that's not a neural network. So all this is doing is taking random noise and reshaping it to look like a grayscale image. So that's just to see how we would train the discriminator. Of course, this discriminator will be able to tell the difference 100% of the time, right? So we generate some real images, we update the discriminator on the real samples, then we generate some fake images, and we update the discriminator weights on the fake samples. So that's one epoch that we put together by hand like that. So you could see that the percentages, it can tell the difference between real and fake 100% of the time. Of course, because the fake images are just random noise at this point. Okay, so that's not very illuminating. It's just sort of setting up some of these training loops and things. Now we come to the generator. Okay.
Does it just say whether 0 is a digit, or does it say that 0 is 0 as opposed to 5?
No, this is just classifying whether 0 is a digit, like from the MNIST database or not.
Okay, thanks.
Yeah. There are, of course, if you can imagine it, it probably exists. So there are, of course, variations of this or elaborations on this where you have what's called a conditional GAN. So it's learning not P of data, but P of data conditioned on some label. And then you can do things like, generate only zeros. And then the classifier is trying to do probably trying to do more than just classify real versus fake. Yeah. Okay, so the generator that we use here is like I said, one of these CNNs in reverse. So I haven't explained to you what the conv2D transpose layer does, but it basically goes from it basically can upsample, can make images bigger and bigger, higher and higher resolution. So so what this does is it maps random noise, that's this latent dimension. That's here, this random noise through a fully connected layer, and then some convolutions, and then outputs in something with the dimensions of an image. Okay, so we use 100-dimensional latent space. Just for reference, the dimensionality of the MNIST data set is 28 times 28, which is like 784, I think. So this is smaller than the dimensionality of the MNIST data set. All right, so we define our generator, which will now sample uniform random noise, 100-dimensional noise, and then send it to an image. So that looks like this. You see, it starts with the input of 100-dimensional noise, and then it maps it to something with the right dimensions that can be reshaped into a 7x7 image. And then with these conv2D transpose layers, we upsample it until it's 28 by 28. Okay, so the generator has about 1 million free parameters. That's what it looks like graphically. All right, and so, okay, so let's see. So we now we have to define the training of this thing. So a lot of this code is the same as before. Here's the fake samples. That's just random noise to begin with. Before we train the generator, the generated samples are just random noise, right? It's like white noise. And here's the GAN. Okay, So here we define the GAN. It has a generator model and a discriminator model. And like I said, we trained them in one after the other. And when we train the discriminator, or sorry, when we train the generator, we have to freeze the discriminator. When we train the discriminator, we have to freeze the generator. Yeah, okay, so that's what's being done here. And so you see there's quite a lot of things to define, right? You have to define these two neural networks and you have to define the model that combines them. Okay, so let me just skip to the, oh, this is the training. We generate some real samples and some fake samples. We update the, let's see, yeah, we update the discriminator model weights, and then we generate some then we generate some fake images and try to see, then we update the generator's weights. Yeah. Okay. Oh, where did I define the loss? Well, the loss is the binary cross entropy. Yeah, so that we never have to worry about. And then there's some subtleties with minus signs that are, obviously very important for getting this to work. But I guess I won't go into that detail. All right, so let's see how this thing trains. So this is after every epoch, just 8 random images are being shown. So you could see after just 2 epochs, after however many epochs, it's starting to take shape, right? This is the generator, after it's been trained for 9, 10 epochs, and maybe some numbers are starting to emerge, right? So this is the GAN trying to learn how to fool the discriminator, right? So we see some 8s emerge. And, so after 30 epochs, maybe we get some 7s, but a lot of them are quite bad, right? 9s, 0s, but lots of garbage too, right? So yeah, I would say it's sort of learned how to do a good job, maybe, I don't know, 10, 20, 30% of the time based on these examples. And the rest of them are clearly, not MNIST digits. So yeah, so I think that's the demo. So that's how the GAN, and it's not going to improve much, from here. And one thing is, I haven't been highlighting these numbers, but these are the discriminator and generator losses. And if you look at them, they're not actually doing much. Like that. So yeah, I don't think I've applauded these, unfortunately, but it's a well-known drawback of GANs that these two losses are, because it's a saddle point optimization. So we're not looking just for the minimum of something. And so these two losses are, and also the way we train them sort of one after the other, alternating, means that these don't really have the opportunity to converge to meaningful numbers. So you can't choose like the best model like we did before based on these losses. You also can't choose the best model based on the discriminator performance. So what people usually do is what we're doing now, which is to choose the best model based on just looking at which epoch gave me the best looking numbers. Okay. So yeah, so that's the vanilla GAN trying to generate MNIST digits. Any questions? I think I did this for 100 epochs. We can scroll to the end.
I have a question.
Yeah.
How come that the generator does not find a digit like 0, which is simpler than, for example, 7, and just only generate zeros?
Oh, good question. Yeah. So in fact, that can happen, and that's called mode collapse, which I'm going to talk about next. Yeah.
Thanks.
Well, the short answer is that if it only generated zeros, then formally this would not be p data equals pg, right? So based on our formal proofs and derivations that we did, that I just reviewed at the beginning of the lecture, that would not be the optimum of the GAN.
I don't quite agree, but if it's only looking at number of digits versus numbers of non-digits, then you don't discriminate between different digits, right?
It would. Oh, no. But it wants to match the probability the GAN loss is optimized when it matches the probability distribution.
Yeah, but probability is defined only as digit versus non-digit, right? You said it's a binary classifier only.
Oh, no. Yeah, good. So let's be clear. The probability distribution we're talking about here, like in the this P data of X. So X is 784 dimensional. It's all the pixels of the image. So P data of X is the PDF on the pixel space. The joint PDF on the full 784 dimensional space. The binary classifier, that's the classifier, or that's the Neyman-Pearson lemma or the likelihood ratio trick. You could just with a simple binary classifier between something drawn from this distribution and something drawn from this distribution, you can learn this likelihood ratio, which then is a ratio of these PDFs on the full 784 dimensional space.
Confusing then, because if it really generates only zeros, it will fool. If it's perfect zeros, it will fool the detector 100% of the time, right? And
Well, you mean if it generates perfect zeros, then the discriminator won't be able to tell difference, right? But remember, the generator. Oh no, sorry. No. Yeah. Okay. If it only produces zeros, the discriminator. Yeah, the discriminator won't be able to tell the difference. So that'll be like 50-50. Right? So wait, what am I getting wrong? So then the generator will eventually decide, hey, if I generate a 1, the discriminator will have no idea. Oh, yeah. So if it only generates zeros, then the discriminator will eventually learn to tell the difference between its zeros and the MNIST zeros. Okay. I'm getting this totally wrong. Sorry. Okay. Too early in the morning. So good. So let's suppose the generator only generates zeros. Yeah, so that could fool the discriminator 100% of the time. But remember, the discriminator is seeing both real images and fake images, like in equal proportion, let's say. So the discriminator, whenever the discriminator will learn, hey, everything that's not a 0 is a real image. So a 1, if it sees a 1 or a 7, it'll say that's a real image, right? So the discriminator loss will not be the generator will not be confusing the discriminator as much as it could be. The discriminator will only be confused when it sees a 0, right? It will not be confused when it sees any of the other digits. So that will encourage that should incentivize the generator to produce all the digits if things are working. Okay, does that make sense? Yeah. Okay, good. All right, so that's how the vanilla GAN works. Now let me talk briefly about problems with GAN training. So why isn't this great? So there are people identified reasons why this is not amazing. Or yeah, another way to say it is, how do we get from these crappy digits to those faces that we're able to at least make us think on that real or fake website? Okay, so let's see. So problems with GAN. So, I mean, the main problem is that this min-max saddle point optimization is unstable. GANs don't really converge, right? You're just going to hit the saddle point. You might stay there for a while, but yeah. And then, there can be many saddle points. So the definition of the optimal one not as clear as in, as in minimization. With minimization, we know we want the global minimum, right? But with saddle points, how do you exactly define the optimal saddle point? Think about, in physics, like with a path integral and, instantons, and which instanton is the one that dominates the path integral depends on your contour of integration, yada, yada, right? So, all right, so GANs have lots of problems with convergence, and correspondingly the losses and accuracy metrics are empirically, there seem to be not reliable for image quality. And so model selection is often done subjectively. And then, so the other thing is that PG of X is not being learned explicitly. So realistic generated examples might not guarantee that PG equals P data. That is, I could get this mode collapse phenomenon where I get very realistic zeros, and then, but the GAN didn't learn to generate anything else. Okay, which is fine, I think, for a lot of natural image applications. Like, say I'm training a GAN to paint paintings, and then I'm going to sell them at the auction house. This actually happened. Like, people sold GAN generated, AI generated paintings for a lot of money. So I don't care if it only generates landscape paintings with cows in it. Like, if I can sell that for $100,000, I'm happy, right? So yeah, for these natural image or real world applications, the mode collapse phenomenon is maybe not as essential, but or not as big of a problem. But in physics, we would care a lot if we're using GANs to generate physics things. Then we want to get the distribution exactly right. Okay. Good. So what is this mode collapse phenomenon? Mode collapse. This is just an example of how it can generate, it can, because this PG of X is not being learned explicitly, this is one symptom of that. And so what can happen here is that the generator and the discriminator can get stuck in a loop. Okay, so it can get stuck in sort of a non-converging cycle, right? So for example, the generator might learn to produce very realistic zeros, and it fools the discriminator. Then it decides, hey, I'm so good at producing zeros, and then it starts to produce only zeros. And then it's like I said, the discriminator realizes all the other digits are not fake. And so the discriminator is not being fooled maximally. And then what does the generator do? Generator switches, it's like a phase transition, to generating another digit. That is, somehow it's easier for the generator to just switch to generating another digit all the time. And then that'll fool the discriminator for a while until the discriminator realizes that all the other digits are fake. So the issue is that, there's some lag time. The training takes a discrete, takes a non-zero amount of time. So if the discriminator could react instantly, then I think this problem would go away. But it takes some time usually for the discriminator to realize what the generator is doing, and it's in that time that you can get stuck in this loop. Okay, so that's sort of how we understand the phenomenon of mode collapse. So another way to, maybe another example is, let's say my data is bimodal, right? So this is the data. Then the generator can learn to just generate this mode, which follows the data very well whenever the data comes from this mode. And then whenever the data, but when the discriminator sees enough data from this mode, it'll realize all these are never generated. Eventually it'll realize that. And then the generator can switch to generating from this mode. And then you can keep switching back and forth. Okay. Any questions about that? So I want to show you another demo. This is really cool. You can go to this link. I think, I'm not sure I sent this link to Krista. So in that case, well, you can take a screenshot, or I'll send this link after the lecture. But what this is these people, where are they based? They are at Georgia Tech and Google Brain. Okay, Google people. They decided to code up this super cool visualization of a GAN. And I think this is just, how many dimensional, I think it's just a 2-dimensional space. They're just visualizing, yeah, a 2D probability distribution in 2D space. So can I fit the GAN to generate data from that probability distribution? So you can pick your probability distribution. Like you can say, this is my data. Okay, so can I train a GAN that generates according to the distribution of points in this data, right? And so you can train it. Let's see, does that, right? So it's training for all the epochs, and it visualizes every single thing in the GAN. So the generator gradients and the discriminator gradients, the discriminator loss and generator loss. You can see plots of those here. Other metrics for how close the probability distributions are. So, and you can see how the generated points purple are after struggling, epoch after epoch, are gradually going to fit this thing. I think the simple thing should be easy to fit, but we may have to wait. So this is really cool, I think. And you can also see that it doesn't, I think even in this example, we may see that it doesn't really converge. Like it'll look like the line, for some of the epochs, but it won't necessarily stay there. Yeah, it's not doing a great job actually. Yeah. So you can also play with the hyperparameters of these networks yourself. Okay, so what I really want, yeah, I guess it's getting better. The purple points are getting a bit tighter. All right, so you can also do other distributions like that. I think you can draw your own distribution. Yeah, so you can draw your own distribution. You can basically make your own scatter plot if you want. So yeah, they really put a lot of thought into this. Okay, I don't. So this is the one I wanted to show you though. This would be mode collapse. Okay, so let me run this one. The data has 3 modes to it, right? And let's see, eventually we'll see once the GAN trains for long enough, it's going to learn to fit one of these modes, and then you'll see that there's like a phase transition and it jumps to another mode. But hopefully this doesn't take too long. If anyone has any questions, now would be a good time to ask. It's like trapped between these 3 modes. It's not doing a great job at all, right? It's really just trying to split the difference between all three of these. So it's, I think it's here. It's trapped at a bad saddle point. So not the real saddle point that we're interested in. Eventually, there should be some kind of phase transition, I think. Yeah, it's really stuck. Well, we can let this run for a bit, maybe. See if I go to another screen, does it continue to run in the background?
So can I actually have a question?
Yes, sure.
I mean, in the training that you've explained, and it seems to work that you train both of them simultaneously. Can we just train one of them and then retrain the other?
Sorry, what was your question? The question is, why don't we train one of them and then train the other?
Yeah, exactly.
Yes. So no, that is what we do. We don't train them to completion though. We train them partially, like maybe a couple of epochs or a couple of mini batches or something. So that's another form of stochasticity. So if you train one all the way to convergence, that's like it's going to run down the saddle, right? So you don't want to train. If you train it all, I mean, there's a runaway behavior, right? So we don't want to train them to convergence completely. So we want to train them just a little bit. Does that answer your question?
Yeah. Thanks.
Wow, it's really stuck. The last time I ran this, it didn't get so stuck. Maybe we should come back to it. I'm going to run it in the background and let's see what happens. So, okay, so unfortunately I did not illustrate mode collapse, but trust me, that is a big problem. So, so I'm not going to have time. I'm not going to have time to really describe this in any detail, but there are ways to improve the original GAN idea. And I think one big class of approaches to improving the original GAN idea is to tinker with the loss function. People realize that the binary cross entropy loss may not be ideal for the GAN, in part because so actually, yeah, I can maybe illustrate that by going back to the previous slides here. Where was it? Here. So the JSD, so we showed that as part of the optimization, formally at least, you get this Jensen-Shannon divergence or distance. And one fact about it that I mentioned is that it's bounded between 0 and 1. So it's 1, it saturates at 1 whenever the data and the generated distributions are disjoint. And people realize that this might not be optimal for GANs because you might want a bigger penalty. So this is like a vanishing gradient problem. So you may want a loss which is sensitive to how different these are. Okay, so once these distributions are disjoint, by any amount, like they could be just slightly disjoint or like very disjoint, doesn't matter. The JSD is 1, so it's just saturated. Then I have no more information about like how close they are, how similar, or how different they are. Okay, so that's at the heart of a lot of these approaches. In particular, something besides JSD, which is more expressive or sensitive to PG not equal to P data. Okay, so JSD is between 0 and 1, right? That's the problem. Okay, so yeah, so one very successful approach, I think, is called the Wasserstein-Gahn, which replaces the discriminator and the binary cross entropy loss. That the binary cross entropy loss is like a difference, is like a measure between the similarity of probability distributions. So they replace that with something called a critic, which uses this something called the Wasserstein distance between, which is also related to something called Earth mover's distance. Earth mover's distance between P data and PG. And the main property of this Earth mover or Wasserstein distance that is important for this, the reason it improves it is that it's unbounded from above, unlike JSD. So the Earth mover's distance is sensitive to, so like this and this, these two, if this was P data and P generated, both of these would have JSD equal to 1, but they would have this Earth mover's distance. Let's say this is scenario 1 and this is scenario 2. The Earth mover's distance or Wasserstein distance as the first case would be much, much less than the Earth mover's distance for the second case. Okay, so this Earth mover's distance is sensitive to how far I have to go, you know, so it has units, I guess. It's sensitive to how far I have to go to get from here to here. Okay, so yeah, so let's see how our, my God, it got stuck. What if I just restart the training? So you see, that's the importance of randomly initializing and retraining over and over again. Ah, see, now it's doing a bit better right off the bat already. It's sort of trying to fit one of these 3 modes. Oh no, it's getting stuck again. All right, we'll come back to that. So, okay, so I'm not going to have time to do any justice to this, but this is an implementation that I did based on some stuff online of the Wasserstein-Gahn for MNIST digits. And it's actually not too different than what we had before. It does require TensorFlow instead of Keras. So TensorFlow is a lower level API that Keras is based on. Okay, so I'm just going to show you the result of this Wasserstein-Gahn after some number of epochs. How many epochs did I do? 200. Okay. But let's see what it is after like 50 epochs. What do you think? How is our Wasserstein-Gahn doing? Better, worse, the same?
Clearly better.
Yeah, I think it's clearly better, right? Still not perfect, but not like those faces, but clearly better, right? Again, there's the question like which epoch to pick. It's not obvious. It might not be one of the later epochs. It might be one of the earlier ones. But yeah, let's scroll to the end. You know, yeah, I'd say all these are roughly equivalent. Still not 100% success rate, but much better than before. And also, if you did a study of mode collapse, you would find, I think that I didn't do that study, but yeah, the claim is that you would find like this is generating the digits 0 through 9 with much better proportions than the GAN. But that would be an interesting little study to do that I didn't do. Okay, so this is just showing you one of the ideas people came up with for how to improve it. And this is just, this is not even the state of the art anymore. And the face thing is using, this is the current state of the art, something called style GAN. Yeah. So again, there's thousands of GAN papers. Yeah. Okay. Any questions? I'm going to talk about physics applications now. All right, so let's talk about physics applications. Oh, how did our GAN lab thing do? Did it get stuck? Oh, it's qualitatively different this time.
Not necessarily better though.
It's not great. Yeah. I ran it before and I saw a mode collapse very clearly, but I don't think that's the thing, it doesn't happen every time. It's all very stochastic. So there it's trying to fit, this is a form of mode. It's trying to fit these two modes and completely ignoring that one, right? It's not doing a spectacular job of fitting these two modes, but it definitely is just totally ignoring that one, right? So, okay, that'll pass for mode collapse here. And then there should be some kind of phase transition where it realizes that one exists and either jumps over to that or yeah, jumps over to that basically. It could take a while for it to realize that though. Yeah, one signature of mode collapse, the phase transition happening is these losses have spikes in them when it's transitioning over to some other mode. So, I don't know if it's possible to rewind the training and visualize. We could let this run and then just go back and look for a spike.
Does it help if you yell at it?
Herbie, it's not a graduate student. Okay, well, anyway, yeah, I should probably, we could watch this all day, but I think we got to move on. All right, so what are some of the physics applications? So I would say, in general, all of the physics applications that have been considered so far, oh, well, no, okay. So there are applications to generative modeling, generative modeling at LHC. And all the applications there have been to simulations, I think. And the main focus is on speeding up simulations. That is, the simulations are computationally expensive because they're trying to do, ab initio physics to basically to compute and sample from P of X, right? So X here could be very high dimensional. Think of a calorimeter image, or what else might we use a simulation for before we get to the calorimeter shower? What about MadGraph, right? Or Sherpa or something. So could also be phase space, many body phase space, right? Or parton shower, hadronization, So lots of particles get produced, right? Each particle has features, and altogether those add up to a lot of dimensions of X. Okay, so what are we doing when we're doing a physics simulation like Pythia or MadGraph, Sherpa, Geant? We are doing usually some kind of ab initio physics, right? We're computing Feynman diagrams or propagating particles through material, nuclear physics and things. We're doing some realistic physics in order to, together with some stochastic processes, right? In order to generate these events. And so these events are going to follow the true distribution as far as our simulation is accurate, but we never, because we generate these things stochastically, we never actually have a formula. It's not like we have a formula for P of X, right? Like there's a lot of random numbers being thrown into this, right? Things are being smeared by Gaussians, or the showering is just some random stochastic process. The splitting function can happen randomly. So all these random numbers together produce P of X. That's what the simulation is sampling from, but we never actually know what P of X is, right? So then the promise of the GAN, et cetera, other approaches too, is that we could fit to observed P of X and then sample from it. So basically the simulated data is following some P of X. We don't know what it is, but we can fit to it, and then we can sample from it quickly and shortcut the ab initio computations.
Do you really improve the statistical error if you do that? I mean, you train it on, say, 1 million events, and you can only learn it to some accuracy, right? Your distribution. And if you generate now with a GAN another 10 million events, it's very fast, but is it really as good as generating 10 billion events from the original physics generator?
Good. Excellent question. You could have written a paper on this. Well, maybe you still can write a paper on this. You could have definitely written the first paper on this question like 6 months ago. Let me find that for you. Gamplifying, I think they called it. There you go. So your friends in Hamburg and Heidelberg wrote this paper addressing exactly this question last August. And so the upshot, I think, of what they found or what they claimed, which is, I think, reasonable, is that indeed, if I train on my GAN on 1 million simulated events, and then I ask for 10 million, I'm not going to get the same statistical precision as if I had simulated 10 million events using Geant or whatever. Okay. However, I will do better. I will get some additional benefit beyond the 1 million that I trained on. And the reason is that the GAN and neural networks in general are interpolating. Okay, they're interpolating between the points that they were trained on, right? So that's what it's doing when it's generating new samples. It's interpolating. It found some fitting function, and then you're interpolating that fitting function to new points. And so the extent to which you had a good fit and enough data, et cetera, is the extent to which this interpolation will give you information and statistical precision beyond what you trained on. Does that make sense?
Yeah.
So in practice, you get some boost to your statistics beyond the 1 million, but it's not the full 10 million that you asked for. But yeah, so that is a problem maybe with this approach to exactly how to quantify that loss of statistical precision. So you're not square root of n anymore, but something else. But the performance gains from this, this is still a relatively new area. So these are all interesting questions for research. And there's enough performance gains from the GAN in terms of speed up that people are motivated to look into that a lot more, I think. Okay, so yeah, but all I wanted to say is that this is the main application so far. There are also other applications to things like unfolding. yeah, other applications too, but yeah, I just want to focus on the face-to-face integration maybe. But I just want to focus on the generating new samples following some simulation aspect. Okay, and the main application is to speeding things up. All right, so and then within that, I would say the biggest speed up that gains that you could ask for, the biggest bottleneck that you could hope to clear out is in calorimeter simulation. So GANs versus Géant. So this is the biggest bottleneck at LHC. So it can take minutes per event using Géant. Okay, Géant is very slow. I mean, it's simulating a lot of stuff, Géant, right? Like all the layers of the detector, even like random material, like loose screws and things, they're all put into Géant, right? So it's doing a lot of stuff. Okay, so but beyond calorimeter simulation, people have also tried to do like event, so parton level event generation, and yeah, I think those are the main two. All right, so let me just show you a couple of papers, all right, in the calorimeter simulation side of things. So I think this is the first paper that used GANs in our field. Okay, it's called CaloGAN. It's by these people, and yeah, so well, okay, sorry. It's the second paper that used GANs. The same group of people had a previous paper that applied it to jet images of the sort that we were looking at, like the top jet images, and I think they did WJet images. So those are not Géant particle showers. Okay, so but then shortly thereafter they applied the same GAN framework to do calorimeter showers. Okay, so what they simulated was a liquid argon detector with 3 layers. So it's not a realistic detector, I think, but it's some example that comes inside of Géant 4. And they simulated positrons, photons, and pions propagating through this liquid argon detector, showering through it. Okay, so they had a pretty complicated GAN. It was not the vanilla thing. Let's see. So this is their structure, because they have 3 layers, and they wanted, to learn, the third layer, as the particle propagates through those layers, each layer is sort of conditioned on the previous one, right? There are correlations between the layers that they need to take into account. So this is it's complicated by the fact that the GAN has to learn basically has to generate 3 images simultaneously that are conditioned one on the other, right? So that's sort of responsible primarily for these complications. Okay, but it's the same adversarial training. You see they have positrons, photons, and pions in a range of incident energies. And yeah, so these are like the average images that they can make. These are what are these? 5 randomly selected images, individual images, and their nearest neighbors in the GAN. So these are all qualitative, assessments. And then they have histograms, which I don't know if you can, is this too small to see? Let me zoom in. So these are histograms of energies, energy ratios. And you could see that, like look at this one, it's completely off, right? This one, the GAN completely failed, right? But a lot of them are pretty good, right? Like here, this blue one is fitting this pretty well, right? Although the yellow one, the pion, is not fitting it well at all. So, it's not perfect. Look, this one got completely distorted, right? and also the pions in general are much harder because this is, oh, I should have said this is an electromagnetic calorimeter. So the pions don't deposit a lot of their energy in the ecal. They tend to go through the ecal. And so it's harder for the GAN, it was harder, I guess, for their GAN to simulate nothing rather than to simulate something, if that makes any sense. Okay, the sparsity plots are completely off, meaning that the GAN is not fitting the 0 pixels very well. Okay, so these are very sparse. I don't know if you could tell from these, but these can be very sparse images, right? Like just 1 pixel turned on. All the other pixels are 0. So the GAN has trouble like reproducing exactly 0. So that's what these sparsity plots are telling you. But this was the first paper of its kind. It was a real seminal work, and it was a very powerful proof of concept for a lot of people, I think. And how do I zoom out? Right. So good. And I think the thing that got people most excited probably was this table. Well, no, I mean the histograms are okay. You know, clearly room for improvement, but a good start. But this table is really caught people's eye, I think. So the Géant 4 simulation of just one of these particles showering through 3 layers of calorimeter took 1.7 seconds. But with the GAN, they could get it down to 0.01 milliseconds. So yeah, so that's like a factor of 10 to the 5. So people thought, oh, 10 to the 5, you know, I could, even if I slow it down by making the GAN more complicated to improve all those histograms, that's a lot of time save or computational savings that I have to work with. So that's you know, that's very exciting. Okay. So that's the CalOGAN paper that was sort of first proof of concept. And then there have been many papers after that, but just 2 to highlight. This was I think this was the first one in our field to try a WGAN, okay? So that was done by these people. Where are they based? I think they're in Aachen. So yes, okay. So the people in Aachen, I think we're the first to try a WGAN on Géant 4 simulations, and they found that improved the performance a lot. They didn't do exactly the same calorimeter configuration as CalOGAN people, but you know, the message is clear. With the WGAN, they got much better plots. I don't know why it's not loading. Yeah, but here, let me zoom in. They don't have as many plots. I wish they had more plots in this paper. They don't have as many plots as the CalOGAN. But you can see that the agreement in these histograms, it's not the same plots either. But anyway, the agreement here is much better. So I think people generally agreed on that. Again, the GAN has trouble. This is like sparsity, another version of the sparsity plot. The GAN has trouble reproducing the sparsity, even here. But look at the very impressive agreement, you know, in all these plots. So this was, okay, this is again sparsity, yeah. But things like energies match very well. So this was considered, I think, a big improvement, and they still maintained, you know, 10 to the 4, factor of 10 to the 4, so speed up. Yeah. Okay, so that's the WGAN.
How do these things compare with the fast parameterized simulation, the data simulation that people
good question.
have used for a long time?
I don't think they have it in here. I've seen it in, there's an Atlas paper, I think that, yeah, I'm not going to try to Google that now, but there's an Atlas paper that, so the experimental collaborations have started to do this as well. And so there is at least one Atlas study of this. And I think they compare against the FastSim. The GAN, oh yeah, another thing I should say is, although the CalOGAN didn't look spectacular, I think, yeah, your question is spot on. It is much better than the FastSim in a lot of cases still. So the FastSim is pretty bad, actually. The FastSim that the collaborations use are like souped up versions of Delphi's, and makes you wonder, like, when we use Delphi's, what are we missing, right? But yeah, so the FastSim yeah, unfortunately, I don't have that, but I can send you the reference later for this Atlas study. Good. Where is the last? Oh, yeah. So the last thing I wanted to show you is the work by these people. Okay, the Hamburg people. So Gregor's group. They are studying. Oh, I should have showed you. Sorry. Too many windows. So the CalOGAN was 3 layers. This WGAN, they moved to, I think, something like 10 layers. I don't know where are these the layers? I think 1, 2, 3, 4, 5. Okay, 7 layers. So they're doing 7 layers with some, decent resolution. And then now the current state of the art for how complicated the GANs are getting is, I think, probably this work. They're doing 30 by 30 by 30. So 30 layers with 30 by 30 resolution. And this is an ILD prototype. So it's not a detector that's currently being used anywhere, but it's a prototype detector for a future detector. And so they're interested in high precision modeling or high fidelity modeling of that with Géant 4, and then with the GAN. And what they found, they took the Wasserstein GAN and added more things to it. So what they found is some architecture that ML people had come up with called BibAE, which is actually a combination of a GAN with something called an autoencoder, which I haven't described to you yet. But yeah, then they were able to get pretty good performance, I think, for this enormous, relative to what's been considered before, this enormous calorimeter simulation. So yeah, again, pretty good agreement. So yeah, that's just to give you a sense, I think, of the current state of the art. They also looked at 2-dimensional correlations between different observables, make sure that the GAN, like all these 1D histograms, don't really capture the full probability distribution, right? It's just a 1-dimensional marginal. The full probability distribution in this case is 30 by 30 by 30 dimensional. So how do you capture that? Well, they did histograms and they did 2D correlation coefficients. So who knows about the higher dimensional correlations, right? But yeah, but anyway, it's doing pretty good. And again, the speed up is still a factor of 1,000 or so, 2,000. So, okay. Any questions? I am way over time for this unit, and I wanted to talk about anomaly detection too. But yeah, let me pause and see if anybody has any other questions.
What was the effort to train this last thing? How many CPU?
Yeah, you'd have to ask Gregor. I think they're just doing it on this GPU here, which is a standard. It has a bit larger memory than we have at Rutgers, so about twice as big of a memory size. But otherwise, it's a standard. This is it's an industrial. It's an enterprise grade GPU. I think it's not like a consumer GPU. But the real test question is, did they need multiple GPUs to train this thing? I don't know. If just one GPU was enough. Yeah. So short answer is it's a lot more complicated, but yeah, also how long did it take to train this thing? I don't know. Did they say? Yeah. It doesn't require like a national supercomputer or anything. It's still being done, with a single computer or a handful of computers that are sitting in their institute. So yeah, so this is the barrier to doing this is not super high. They even have a GitHub that you can clone and do this yourself on your own GPU. So you don't really need like special. Well, you need a GPU, but you don't need a super high level. Okay, they don't seem to say anywhere. Yeah. I myself have not tried to do this one. I have reproduced the CalOGAN results, so that's doable, very much feasible on a GPU, single GPU. Anomaly detection and searches for new physics. at the LHC. Okay, so, just by way of motivation, I'm going to be pretty brief on that because of the time. We all know we're looking for new physics at the LHC. And so where is the new physics at LHC? We haven't found it yet, and we've been looking for 10 years. One possibility is it's not in the LHC data, but there's a lot of LHC data, and we haven't looked everywhere. So I think it's too early to conclude that is what's going on. And so currently what we've done is we've done many model-specific searches. So existing searches, probably, I don't know, thousands of model-specific or mostly model-specific searches. Okay, more and more of these searches are being done also with machine learning. Okay, so cut-based and increasingly with ML, but in the categorization of things that we've discussed in the first lecture, these would fall under the category of supervised. That is, we know what we're looking for, something specific. We think we know what we're looking for, and we're optimizing our search usually with simulations of that signal and also simulations of the background. And so whether cut-based or ML-based, we're training our search strategy with truth labels. Okay, so it's a supervised approach. But what if, so model-specific searches motivated by cool things like supersymmetry, extra dimensions, etc., right? So, but what if we don't know what we're looking for? Right, so before the LHC turned on, many of us, including myself, were so convinced that we would just discover a gluino and, like it would just have no background and it would just be poking us in the eye. And then the rest of our careers would be spent measuring the properties of the 100 new particles that would be discovered at the LHC. So unfortunately for me, I drank that Kool-Aid for a while. So now I'm increasingly motivated, a lot of us I think are to entertain the possibility that maybe, although all this development of supersymmetry for all these decades, we don't actually know what we're looking for. And is it possible, okay, so we've done thousands of model-specific searches, how well have they covered the parameter space? Okay, so is it possible that they haven't covered the model space very much or enough, and that there could still be new physics hiding in data, we just haven't looked in the right place? So I think the answer to that is yes. And so if we don't know what we're looking for, then that's a very tantalizing possibility. Can we design searches for new physics that are more model agnostic? So that's model agnostic searches for new physics. So we need model agnostic searches for new physics at the LHC. Okay, and as you may have guessed, this is a ripe target for unsupervised, or at least less than fully supervised or weakly supervised or semi-supervised ML. Okay, I'm not sure I went through and defined all these different forms of supervision for you. So in case I didn't, let me just remind you at least. So unsupervised means training with no labels. Okay, so fully unsupervised means no labels are used in the training. So it's just data. So the GANs, for instance, are an example of this, right? We've already seen unsupervised ML. That was the GAN is an example of this. The GAN is trained just on the data, right? And yes, we create these labels of fake or real, but that's just an auxiliary thing, right? That's not a real label that we care about in the, you know what I'm saying, right? So we're training the GAN on the data itself, and the labels are not being used. The data is not labeled. Every data point is assumed to be, you know, drawn from one overall distribution. Okay, makes sense? So, right, so that's unsupervised. So weakly supervised is training with noisy labels. So just an example of, okay, so what does noisy label mean? It means that the label correlates in some way with what you're interested in our case, new physics or standard model, okay? But it's not exactly, we don't know, because it's still data driven in this case, we don't know that whether it's for sure new physics or standard model, okay? So the labels are noisy. They're not exactly what we want, but they correlate with it somehow. So that's weakly supervised. And then semi-supervised is training with a mix of labeled and unlabeled data. So maybe you'll train your algorithm on some simulated signals and backgrounds and also some data. And you hope that, you know, the simulations are biased or just model specific, but then you train that to learn something about the difference between background and the signal, maybe, and then you go apply it to the real data and look for find what you find, or something like that. So that's semi-supervised. Okay, so these are all things that are actively being explored right now, and there's lots of ideas out there. Okay, I'm not going to be able to review all of them, but I'm just going to give you a couple of examples of some things that are being tried. Okay, let's see. So yeah, just to give you one example though of a signal, this is a signal that's motivated a lot of my own work. I really don't care about this model. It's not motivated by anything top down or anything, but just as an example of a new physics scenario that could be hiding in the data. Okay, so this is almost sort of pulled out of a hat, but consider the following. So I have a Z prime with mass, multi-TeV, let's say, which decays to two, I don't know, scalar particles, and those scalar particles can decay to jets. Okay, and suppose mx and my are much, much less than mz prime. So I claim that this scenario could be hiding in the data right now with like 10 sigma significance, but we would have missed it. And the reason is there is no explicit search for this at LHC. So there's no model specific search that's optimized to look for this. And if you scroll through the list of all the searches, I'm pretty sure that, I've done this exercise. I'm pretty sure, of course, I haven't paid attention to everything, but I'm pretty sure you will find that the only thing that's sensitive, okay, so what does the signature look like? Because X and Y are much lighter than Z prime, the X and Y are going to come out highly boosted, okay? And you're going to get a two-pronged jet, okay? So X and Y come out highly boosted. They're not displaced decays, they decay promptly.
Do you care if X and Y have different mass or not?
Yes, we do, actually. Good. Okay, I'll get to that in a moment. And mx not equal to my, or we allow for the possibility that they're not equal. Okay, So the signature here looks like two large radius jets. Okay, these are highly boosted because they came from the Z prime that's much heavier than them. The Z prime is more or less produced at rest, and so these are coming out highly boosted. And so they're two-pronged substructure. They're like W bosons basically, and they're going to come out in a large radius jet. So two large R jets. Okay, and so the only search that would be sensitive to this is a dijet resonance bump hunt. So there's a vanilla dijet resonance bump hunt, the classic one that's always done. That would be sensitive to this, right? Because these two large radius jets would be included in this dijet resonance bump hunt, and they would make a bump at the mass of the Z prime, right? So M, so they call this J1 and J2, M, J1, J2, you know, you'd see a bump at the mass of the Z prime. However, this dijet resonance bump hunt would not be very sensitive to this. There's a lot more structure going on, like the mass of the X, the mass of the Y, the two-pronged substructure, et cetera, is the only search that would be sensitive. But that would include this that could see the signal, but not optimized for it, right? So there's many more handles. For example, you know, the mass of the X, the mass of the Y. Oh, sorry, I should write them in terms of the things you can actually see, like the mass of jet 1, the mass of jet 2, the two-pronged substructure of jet 1, two-pronged substructure of jet 2, etc. Right? Okay. Yeah, it's important that we allow these to be different because there are searches for RPV squarks, for instance. So if I pair produce squarks and they decay to two jets through R parity violation, then there are searches for what are called paired dijet resonances. But they all assume that the two squarks have the same mass. And they don't assume that the squarks came from a Z prime. So two differences. But yeah, if these had the same mass, the paired dijet resonance searches could in principle be sensitive to this, but still not optimized because they wouldn't require that they make a resonance that's the Z prime. Okay, so the claim is that I will show you evidence for in a moment is that this could be sitting in the dijet resonance bump hunt with say 1 or 2 sigma significance. That would have shown up in this with 1 or 2 sigma significance. But if you do the right kind of unsupervised or weakly supervised search, you could find this with a factor of 10 more significance. So 20 sigma or 10 sigma significance by using all these other handles. Okay, I hope I have enough time to get to that. Let's see. So, but that's just an example of how we are not looking everywhere right now. Any questions about that? All right. So yeah, okay. So in the unsupervised, so fully unsupervised approach is, yeah, okay. So hold on, show you one thing. So a lot of what I'm going to tell you is based on the LHC Olympics, which I helped to co-organize together with Gregor and Ben Nachman. And this was a data challenge that we put together with some black boxes. So fake data that contain standard model, background, and possibly new physics, and asked people to develop anomaly detection strategies to find the new physics. So all the boxes have been opened So we told people, so the challenge is over, but the data is still there. And if you want to play around with it, I highly recommend that. It's still, I think it's still very stimulating and useful. All right, so let's see. Yeah, a lot of, we did not update. Oh gosh. We did not update the, oh, here it is. Okay, thank you. So yeah, so we put out a community white paper here, which you can, I recommend you check out. And it has a list of all the approaches that were, these are all the people that participated in the data challenge. And these are all the approaches that they tried. Okay, so this is a pretty nice, I think, snapshot of the current state of the art. And you can see we organized it into these three categories: unsupervised, weakly supervised, and semi-supervised. Okay, so now I'd like to take you through just a couple of these examples. Not completely unbiased view of this stuff. Two of these examples I myself have worked on or invented. And another one is a very powerful one that's very quick to explain. So, okay, so I'm gonna take you through something called an autoencoder, and then I'm gonna take you through koala hunting and this thing called Anode in 20 minutes. All right, I'm gonna try. I would highly recommend you check out the LHC Olympics 2020 community, I guess, community white paper. And actually this signal, it's not just totally pulled out of a hat. We use this as our R&D signal for LHCO 2020. Okay, so you can download, and I will show you a demo where I download this data from our LHC Olympics website, simulated signals on top of a background of this type. Okay, so fully unsupervised approaches, you can get a more complete list here, but one example is this thing called an autoencoder. Okay, and what the autoencoder, it's from the ML literature. Okay, so this is something which ML people came up with, has been around for a long time, and has many applications, including to anomaly detection. People use this in the real world to look for things like credit card fraud, apparently. So when you get a call from your bank asking you about a suspicious charge, they very well may have run an autoencoder on your purchase history. I had a postdoc a few years ago who got a job at Capital One, I think it was, and as part of their interview, they were asked to do this credit card fraud challenge, and they used an autoencoder and then got the job. So anyway, so this has long-standing applications to real-life scenarios. And so in 2018, I think it was, yeah, 2018. So do I have any references to my own work? Yeah, okay. So Heimel, Gregor, Tillman, and Jenny Thompson, in 2018. And so on the same day, we coordinated my two postdocs, Marco Farina, Yuri Tronakai, and I. We put out papers, yeah. We put out papers saying, hey, why don't we try this method out to look for new physics at the LHC? Okay, and what the method is, in a nutshell, is we train a ML algorithm to map X in the data back to itself. So, and that sounds trivial, why doesn't it just learn the identity mapping so we pass this through a bottleneck. So it's a lossy ML algorithm. Okay, so we enforce some kind of compression on the input data. And so it has to pass through a bottleneck, which is called the latent space. Call this thing Z. Okay, so the idea is that the ML algorithm, the autoencoder, is forced to learn some latent description of the data, which can describe the data the best. Okay, so it's like a non-linear version of principal component analysis, if you've heard of that before. Okay, so the loss that we would train this on is some measure of the distance, a difference between the input and the output. Okay, so like the mean squared error is a very common choice. Okay, and so if you've trained this autoencoder to reconstruct the data and to learn the latent features hidden inside secret latent dimensions of the data that describe its variance, then the idea is you can use this for anomaly detection as follows. So if I train the autoencoder on mostly backgrounds, so let's say it sees, in an extreme case, let's say it sees only backgrounds. Okay, so then it'll learn to reconstruct the backgrounds well. So if this is the, so this is called the reconstruction error. That's the loss. And with some kind of compression, this reconstruction error will be minimized from instance to instance in the data, but it can't be exactly 0 for every data point. Okay, so if I make a histogram of the reconstruction error for the backgrounds, it might look like this, right? Mostly 0 or close to 0 with some tail, right? And then when AE encounters a signal, so let's say the signal is rare, then in an extreme case, if it's only been trained on backgrounds and then you feed it some signal that it hasn't seen before, that's not in the background sample, then the AE won't know what to do, how to reconstruct it. And so for the signals, it'll produce a much larger reconstruction error. Okay, and then we could use, a cut on the reconstruction error to define the anomaly score. So L greater than LC is an anomaly threshold. So that's the basic idea of the autoencoder for anomaly detection. Any questions about that? Have I completely lost everybody, like at some point? So let me show you a demo that I prepared for the autoencoder. Let's see. All right, why doesn't that pull up? Oh, it's over here. Wait, okay. Close that. Ah, here it is. No. Okay, where did it go? All right. Ah, here it is. Okay. Yeah. So here's a tutorial for the autoencoder. And let's see, what am I going to load here? So these are the jet images of TOPS versus QCD. Okay, so let me just give an example. So example from both the Heidelberg groups and my paper can train an autoencoder on QCD jet images. And it can discover top quarks as the anomaly. Okay. So of course we have discovered top quarks already, but this is a nice little proof of concept of the way that the thing works. Okay, maybe I won't, in the interest of time, I'm not going to download all this and train it, but you can do this at home. So we're downloading the jet images. There's another section here that I don't have time to explain. It's a different anomaly detection approach. Okay, here's the autoencoder. All right, so this is the geometry or the architecture of the autoencoder. We are gonna send, it's just fully connected. Okay, so we send the images to a fully connected neural network, which has these two hidden layers of decreasing size, and then to this intermediate layer of size 6. And it's just 6 nodes. So this is the latent space. Okay, so we're mapping all the images to a 6-dimensional latent space. Idea is that these 6 features that they map to should describe the jets as much as possible. So, you know, if it was physics, these features would be physics observables like jet mass, you know, and subjettiness, etc. But of course, the autoencoder can learn whatever it wants to in order to describe the data well. Okay, and then after the latent space, so this is called the encoder, and then the decoder maps it back to the original image dimensions, which are, it's 20 by 20, these images. Okay, so good. And so we're just going to train it on only the backgrounds. Okay, so in practice, you would actually, you know, if this is data driven, you would train it on the data. And then the presence of a little bit of signal would not affect the results much. But just for simplicity here, we're going to train it just on the background. Okay, and so it's learning to minimize the reconstruction error here. And then let's look at the reconstruction error for QCD, which it was trained on, and for TOPS. Okay, I hope I have that plot loaded here. Okay, good. So this is what you find. All right. So this is like I promised. So the QCD reconstruction error peaks at some small number, 10 to the minus 4 in these units. And then the TOPS, on the other hand, you know, peak at a higher value, right? Because the TOPS are different than the QCD jets it was trained on.
Still pretty small though.
Yeah, pretty small, but still big enough to have an effect. Okay, so how do we measure the performance of this anomaly detector? So for that, I want to introduce another metric called the significance improvement curve. So this is a useful metric for anomaly detection. Is the significance improvement. And that is the true positive rate. Oops. So the true positive rate. So let's say I do a cut on my anomaly score. Let's say I have an anomaly score, something which tells me I have an anomaly or not. I do a cut on it. So that defines for me a true positive rate and a false positive rate. And the significance improvement, so you could, maybe you're more used to thinking of it as a signal efficiency and a background efficiency. Okay, so that's the significance improvement. And so what is this metric, or what is this telling us? So this is saying that, so let's say my initial significance, so before any cut, I have S signal and B background in the data. Okay, so what is my initial sort of nominal statistical significance of the signal? Anybody? Just let's say both S and B are large. Okay, so things are, yeah. So what is my nominal statistical significance? Anybody know?
S over root B, right?
Good. So initially I have S over square root of B before sigma is S over square root of B before any anything. Okay, so after anomaly detection, so after a cut on my anomaly score, what do I have left? Well, my S got multiplied by epsilon S, my B got multiplied by epsilon B, right? So after anomaly detection, I have sigma, so this is sigma before, this is sigma after, the significance after is S over square root of B times TPR, let me write in terms of these efficiencies, nicer to look at, epsilon S over square root of epsilon B, right? So it's sigma before times the significance improvement. Oops, what just happened? Where did my, there it is. Okay, so yeah, so that's the purpose of the significance improvement. It's a metric which is independent of how much signal and background I actually have in the data, and it tells me the factor by which my significance of my new physics would improve by after doing the anomaly detection. Okay, it's all nominal, you know, very naive statistical significance, but yeah, it's still, so it's some metric. Okay, make sense? Good. So so that's what I'm going to plot now for you. So as we cut on this anomaly, as we cut on this reconstruction error, we're going to get a significance improvement curve that looks like this. So I'm plotting here, I didn't label the axes, sorry. This is the true positive rate, so the signal efficiency, and this is the significance improvement. So you can see that you can enhance the nominal statistical significance of the tops by a factor of 2 using this reconstruction error as a cut. Okay, while keeping about 80% or 60% of the tops. So, you know, that's not nothing. And considering that we didn't put in anything about what we're looking for, let me just emphasize that, right? We trained the autoencoder just on the QCD backgrounds, and we didn't say we're looking for tops, right? So that's the whole point of this kind of thing, is it's not going to be super optimal. Obviously, if I train a top tagger, I would get a much better result. But this is, in principle, capable of finding many different things, okay? So the purpose of this anomaly detection is to cast a wide net and not be over-optimized to any particular thing. Okay, so there's a trade-off there. Any questions about that? No? Okay.
How does
So
this
that
scale
is just,
with the latency?
go ahead.
Sorry, how does this scale with the dimension of the latency? This going down to 6 or 6 seems awfully
Excellent
small.
question. Yeah. So in fact, yeah, in my course, I had the students as a homework exercise play around with the size of the latent space, right? So this is very fast to train. Each epoch's like a second. So you can quickly scan over the latent space and see how it depends. So, you know, basically, so let me add that here. Homework, explore dependence of anomaly detection performance on latent dimension. But as you make this wider and wider, keep in mind you also have to make this wider and wider, right? Because otherwise that'll become the bottleneck. But as you make these things wider and wider, it can just learn the identity matrix, identity mapping at some point. And then you don't expect this performance to be as good. On the other hand, it will never perfectly reconstruct the background. So there will always be some anomaly detection performance. Okay, so it's not going to completely go away necessarily. That is, this thing will scale to 0, but it won't be exactly 0. So some of it is just a rescaling. Yeah. Okay. All right. So let's see. I'm going to go a little bit over time, if that's all right. Do people have somewhere to be right, like right now?
Always.
Huh?
Always.
Always. Okay. Well, yeah, I'm just going to take
So
like,
it's okay. It's okay.
yeah, I'm just going to take another 5 or 10 minutes, if that's all right,
That's fine.
because I really wanted to tell you about these other approaches. So, all right. So the autoencoder, it was a relatively early idea, I would say. And, you know, it's nice because it's fully unsupervised. And so in principle, it could find many different things. However, the flip side of that is it's going to find what it finds, right? And there's sort of there's no guarantee of any kind of optimality. And so, yeah, so that's the trade-off. And so I think it's very interesting also to think about approaches, alternatives to this, where you maybe sacrifice a little bit of model independence, okay? And in return, you get some kind of optimality guarantees. So that is the promise of weak supervision in general. So here we would like to train. So basically here we'd like to assume something about signal and or background that allow us to define noisy labels and get more sensitivity to the signals that satisfy these assumptions. Okay, so I'm being very vague, but let me give you an example. So the example is this bump hunt again. Okay, so suppose I have my MJJ and I want to do this bump hunt where the signal lives in some signal region. Okay, so this is the signal region and these are the sidebands, right? So if I assume that the signal lives in the signal region and that the background is smooth in MJJ, so 2 assumptions, then I can do many more things. Okay, then I can do weakly supervised approaches. Okay, but of course, if I just have MJJ, I'm just doing the vanilla bump hunt. The reason this becomes more interesting or more sensitive is that there are other features in the data besides MJJ. So let me call these other features X. So maybe X is, like we said before, MJ1, MJ2, and subjettiness. Okay, so the reason that we can get more from machine learning beyond the vanilla bump hunt is because of these extra features where the signal may be localized and the data is again, the background is again smooth. Okay, so if this is the signal, then we can develop algorithms, so weakly supervised or even, more than that, so less than fully supervised algorithms to identify where in the auxiliary features, these additional features, the signal is localized. Okay, so that's what's happening in the R&D data set, right? So in this example, the signal is localized in these 2 masses and in the n-subjettiness variables. So so something like the vanilla bump hunt completely misses that, but we could train a more powerful algorithm to find the signal also in these auxiliary features. Then that's much more powerful. Okay, so yeah, so I guess there's two approaches to that I want to talk about. But before, yeah, I guess there's one additional point I want to make, which is that there's an optimal discriminant for anomaly detection. This is where the optimality guarantees come from. So that's the likelihood ratio, which is a funny between, yeah, okay. So let's consider this likelihood ratio. So I want to think of anomaly detection as a hypothesis test between between data and background. Okay, and how does that make sense? So this is a model for the data, and this is a model for the background. So it's not the actual data distribution, but a model for the data. So then I want to ask, does my real data fit the model, my model for the data better, or does it fit my model for the background better? Does that make sense? So I can use this hypothesis test to reject the background hypothesis. In other words, I can say my data looks more like my data model than it does like my background model, which means my data model and my background model differ from each other. And that would be the sign of something deviating from the standard model. Okay, so there are two, at least there are more than two, but I want to tell you about, at least sketch two approaches for how to get this likelihood ratio. Okay, so one approach is called the classification without labels, which has the abbreviation koala. And the idea here is that we train a classifier on signal region versus sideband data. So if this classifier is optimal, what will it learn? So it'll learn this likelihood ratio. So sideband is here, signal region, sorry, you can't see my place. Sideband is here, signal region is here. And X are these auxiliary additional features. So let's think about what this means. So the numerator is just the data distribution. What about the denominator? So the denominator is the distribution of these features for data in the sidebands. So I'd like to say that that's the background distribution, but in order to say that, I have to make one additional assumption, which is that these features don't care about whether I'm in the signal region or the sideband, in the background. So this is equal to this, the desired likelihood ratio, if X is independent of MJJ for the background. Okay, so that's an assumption about these features that has to be satisfied in the background, in the standard model background, in order for this koala method to work. Okay, but if that's satisfied, this method is very simple to implement. All I have to do is train a classifier on these two subsets of the data, and then it will go and find this signal if it's working.
Can't I go a little bit more general in saying that the X dependence is linear? Because at least if you do then symmetric sidebands left and right, then shouldn't it average out?
No. If it's linear, that's bad, because once the classifier can learn the difference between signal region and sideband is just, let's say it's linear, so that these X features depend linearly on where I am in MJJ. Then the classifier will just figure that out like that, right? And then it will tell you 100% of the time that you're in the signal region or in the sideband based on this value. So the fact that it's linear doesn't matter. It's not you know, it can learn a localized thing, right? It will learn this window cut. It'll say, you know, so okay, let's say the x's depend linearly, which means what in practice? It means that in my x space, like the sideband data might look like this, and then I need a different color. You know, the signal region data might look like this. That would be linear, right? So like when MJJ is less than something, the x lives here, and then as I slide MJJ over, I'm sliding x over as well, right? So this would be signal region, and this would be sideband. So then the classifier will learn this, right? Learn that anytime it sees x here, it's signal region. Anytime it sees x here, it's sideband. But so then it will not learn that the signal is here, right? The difference between this effect is much bigger than the small amount of signal that lives here, and so it won't be able to pick up on the signal. Does that make sense?
Yeah, sounds reasonable.
Okay, so I'm just going to show you a demo of the koala method real quick on the R&D data set. But before I do that, there's another method, which is more complicated. So sorry, this is Collins, Howe, and Nachman. And there's another method which Ben and I came up with, anomaly detection with density estimation, or anode. Okay. And it's more complicated. It involves something called density estimation. So it attempts to learn the numerator and the denominator of this likelihood ratio directly from the data instead of a classifier. Okay. So it's not likelihood-free inference, but so that makes it maybe less, more prone to sort of mistakes in the modeling of the data. However, it allows you to relax this assumption that these features are independent of MJJ. Okay, so what anode does is train a density estimator. So I haven't told you what those are. I didn't have time, but a density estimator can learn P of X explicitly. So learn P of X of the data explicitly. So unlike a GAN, you can fit basically a neural network to the data and get a function which should match the P of X in the data that the data was drawn from. Okay, so it's a much harder task than the GAN, which has to learn things only implicitly, right? So, but there are families of neural network algorithms, neural network-based algorithms that can do this to varying degrees of success. It can learn P of X explicitly. In particular, we use something called the normalizing flow, which is a very cool technology. But unfortunately, I ran out of time. I don't have the time to explain that to you. But so these density estimators, let's posit that they exist. Then we can train one on the signal region data. Actually, this is a good example. So we can train one on the signal region data. So we train a conditional density estimator, condition on MJJ in the signal region. Okay, that's the first thing. And then we train another one conditioned on MJJ in the sideband. Okay, so this is equal to P data, and this is equal to P background in the sideband, right? But unlike koala, because we have these two things explicitly, separately, we can now interpolate the latter one. That's like what you were suggesting, I think, Manuel. So because we have control over this one separately, we can now interpolate it into the signal region. And so then we get P of background for M in the signal region. And then we can construct this likelihood ratio, P data of X for M in the signal region and P background of X for M in the signal region. Okay, so this involves many more steps. Training these density estimators is not an easy task. So I don't have a demo for you for that, but yeah, so that's the price you pay, and what you gain is that you don't have to make this assumption that X is independent of MJJ in the background. All right, so the last thing I want to show you is a demo of how Koala works, and just to illustrate for you the statement that this R&D data set could be hiding in the data. And with the right technique, we could pull it out with much more significance. Okay, so here's my implementation of the koala hunting method. Here's the reference to the original paper by Jack and Kyle and Ben. Here's where you can download the R&D data set features, okay? For background and signal, there's a little bit of post-processing of these features. We provided people these features with the 3 momenta and the jet masses and then subjettiness. And so there's some post-processing you would want to do. Okay, so here's a plot of the features. Oh, sorry. So here's MJJ. Okay, you see that the signal lives at MJJ of 3.5 TeV. Okay, this is a lot of signal. So we provided people with up to 100,000 signals and 1 million backgrounds. Okay, and I think actually I normalized these plots. Did I normalize it? Yeah, I normalized these plots to unit area. So it looks even more than the real amount of signal would be like this tiny amount, this little blip here. Okay, I don't know if I have a plot of that, but I mean, not the real amount. A realistic amount of signal would be a tiny little blip here. Okay, so these are the other features. So the mass of jet 1, the difference in mass of jet 2 and mass of jet 1. So the X and Y bosons live at 100 GeV and at 500 GeV. Okay, and here's the N subjettinesses for the 2 of them, for the 2 highest PT jets in every event. All right, for signal and for background. All right, so these are the features we'd like to train Koala on. Okay, so now we're going to take a tiny subset of those 100,000 signals. We're going to put 1,000 signals into a background of 1 million QCD jets. So that's an S over B of 10 to the minus 3. Okay, we're going to define a signal region and a sideband. So like so. And so here's the amount of signal that actually lives in the and background that live in the signal region. It's about 120,000 backgrounds, 770 signals. And so the starting significance is 2.2 sigma. Okay, so that's, and this is what you would nominally see if you just did the dijet resonance search, right? The vanilla bump hunt would, if it had a perfect background estimation, you know, no Poisson fluctuations or anything, it would get a nominal significance of 2 sigma. Okay, so that's not something we'd be very excited about, right? In the vanilla bump hunt, 2 sigma excess. All right, so now let's see what happens if we apply Koala to it. So we're gonna take the signal region data, okay, which has a little bit, you know, the 700 signals in them, and we're gonna take the sideband data. And we'll just use balanced classes for the 2, even though, you know, there could be a lot more events in the sidebands. We're going to use balanced classes, and then we're going to train a simple super dumb classifier on them. So just some small number of hidden layers, 64 nodes each. Okay, not a lot of parameters or anything. 12,000, 13,000 parameters. It's just a classifier. Okay, for this small number of features, we could probably also just feed it to a BDT. All right, so we train this thing for some number of epochs. And look at what's happening. So the accuracy of this classifier is close to 50%. What is that telling us? Is this a good thing or a cause for alarm? What does it mean that the classifier cannot tell the difference between signal region and sideband, it appears?
Probably good. Means that the sidebands are the same as the signal region, right? For the
That's what you
most
want.
of the
Yeah.
events.
So right. So the signal is so small that it's going to show up maybe in the 4th decimal place here in terms of the accuracy. So, yeah, what you want to see is a classifier that's having a lot of trouble distinguishing between signal region and sideband. Okay, so that's good. And the validation accuracy is also fine. So good. So now, okay, it trains for 50 epochs, pretty fast. You could do this at home very quickly. And now let's look at some performance. So we're gonna, the model predictions, we collect the model predictions. Let's look at the performance of this classifier on signal region versus sideband. That's what this is. So this is the ROC curve, which is just a diagonal line. And that's the sign of a pretty random ROC curve, right? It can't tell the difference between signal region and sideband. Okay, that agrees with the 50% accuracy, right? Now, let's ask a different question. Let's now feed it the truth labels, signal region or, the truth labels are signal or background, right? So now we're going to use the fact that this is an R&D data set where we have the truth labels. The truth labels were not used in the training, right? But we're going to now peek under the hood and see how well does the koala classifier find the signal, given that we know what the signal is, okay? So this is not cheating, it's a metric, right? It's important that the truth labels were not used in the training of this thing. But if we ask for the ROC curve that way, using the truth labels, this is the SIC curve we get. Okay, this is probably a low statistics fluctuation, but this part here should be reliable. So what is this saying? This is the SIC curve versus the true positive rate, so the signal efficiency. So we can keep about 50% of the signal with some cut on the koala classifier, and we can enhance the significance by like a factor of 7.5. Right? So we can take this 2 sigma excess in the vanilla bump hunt, and we can enhance it to nominally 15 sigma. Right? Of course, by that point, you're probably systematics dominated. But yeah, the statistical significance would be very, very robust. Right. And so that's the basis to a large extent of the claim, you know, that there could be new physics hiding in the data, and we just haven't looked everywhere yet. And we certainly haven't looked in the right places yet. And there's a lot of unexplored discovery potential, untapped discovery potential left for these ML techniques.
Sorry, isn't it more like 7.5 sigma? Because you've lost half your signal too.
No. So this is the true positive rate divided by square root of false positive rate. So it
Yeah,
really
but
is.
you, at the point where you have 50% signal efficiency, right? Then there's only half of the signal left.
Yeah. So I took that into account, you know. So
It's a ratio already. Okay. Then it's fine.
Where did I write that metric? Yes, here. So it's multiplicative.
Okay.
Yeah, that's the whole point.
Okay.
You know, so no matter what S and what B I started with, this is a multiplicative factor of the enhancement. Yeah. So this was 2 to begin with, and this we're plotting is like 7.5. So the sigma after will be 15. Make sense?
Yeah, so it's not a ROC curve anymore, that thing.
Right. Yeah. That's why this is better, I think, in my opinion, to plot than the ROC curve, because this really tells you right on the head how well your anomaly detector is performing in terms of discovery potential. With the ROC curve, I mean, it's neither here nor there. Yeah. So yeah, I think that's, you know, sorry for going a bit over time, but and there's so much more I could tell you about, but hopefully that gives you some idea of what's going on right now in this very active area.
Yeah, thank you very much. So maybe there's some, well, the detailed questions to today, or also even some broader questions just for, you know, where the field is heading or something like that.
But for this last thing, maybe immediately, you would have to do that for every single bin, something like that, right? That is now for one hypothesis for the signal mass, right? You would have to do that for scan through the MTJ to.
Ah, good. So yes. So okay. So right. So we would have to repeat this for each window in MJJ, just like you do for the vanilla bump hunt, right? The standard bump hunt. However, you would not. It's important that we're not scanning over any kind of like boxes in these 4 additional features that the koala was trained on, right? That's happening with the classifier. It's that the classifier is doing this essentially itself. So the look elsewhere penalty or the trials factor penalty that you pay for this method should be just the usual one from the bump hunt. And there's no additional trials factor penalty from this 4-dimensional space. Yeah, which you would, if you did like a cut-based thing where I looked for excess, I did a cut and count in bins of MJ1, MJ2, tau2 1J1, tau2 1J2, there would be a huge trials factor, right? In the cursive dimensionality. And presumably that's not, we're not paying that price here with this method. Although, that study has not been done really, it's kind of an expensive, computationally expensive study to do. You'd have to really do like pseudo experiments and train, millions of these classifiers probably. But yeah, I think you're not paying that price the same way here. So I think it's not bad.
Thanks.
Any other questions or, just inquiries or so about?
Yeah, random thoughts, concerns, skepticism, anything.
I mean, would you say this has taken hold now in the Atlas, in the LHC experiments?
What's this?
Well, this approach, I mean, are they starting to use this,
You mean anomaly detection specifically? Like
Yes.
the thing I just talked about?
for searches, yeah.
Oh, yeah. So, this Ben is on Atlas, of course. And so he pushed through just recently the first koala hunting search on Atlas.
Okay.
So, but it was sort of a baby version of it because they only use 2 features, the 2 jet masses, MJ1 and MJ2.
Okay.
And
so
yeah,
it's
but
really,
it was,
it's really just starting, right? It's really.
it's just, yeah, but that was a huge effort, I think, to get that through the collaboration.
Yeah.
Even though they only use 2 features, MJ1 and MJ2, and making sure they understand their p-values and their false positive rates, their systematic errors, of course, all these things. A lot of effort went into that, I think. But now that they got that set up, I think they can now turn a crank and do koala-like searches with all sorts of different feature sets.
They must have done this analysis of the look elsewhere business then, no? For that.
Well, yeah, I think for that, they must have done something like that, although, I'd have to look at the paper to see what they said exactly. Because, yeah, to quote a p-value, well, I'm not, if they quoted a global p-value, then they must have done that. I don't remember if they did quote a global p-value. I mean, they didn't find anything, so they set a limit. Guess to set a limit. Actually, to set a limit, yeah. Are limits set with local or global p-values? I have to think about that.
Set a limit as a function of MJJ, right? So
yeah.
Something that's
so it's local, I think.
Yeah,
so it's possible they didn't have to calculate any global p-values. Yeah. Any students with a thought or a question or anything?
Okay.
Yeah, I should say, I think this is the future, like this stuff here. People are going to keep doing the supervised searches, but this is the growth area.
Yeah.
And I know it's certainly like my dream and many other people's dream that there would be, like right now at the LHC, there's a SUSY group and an exotics group, but there's no model independent search group. And the number of
exotics group, right? But
no, but everything they do is still like model specific.
Yeah. There is the, I guess, EFT approach is the alternative, but that's at least an attempt to.
Yeah.
I guess you could take EFTs and just directly compare them to standard model data. I mean, I think that's, in some sense, that's related to what John Butterworth is doing, right? But,
that's another kind of model independent search. That's true.
Remember, there was some very old, many years ago, CMS, I think, tried some sort of model independent search for anomalies, but I think they just looked off through histograms or something. I forget how it worked exactly.
Yeah, so if I had a longer version of this talk, I review the history. So literally there is one CMS analysis that does a model independent approach and one atlas. And they do the same thing. They look at all possible histograms in all possible bins. They bin the data up into like 17,000 bins or something. And they look at every possible histogram and they compute a difference between data and simulation in each one. So, you could find something that way. Huge trials factor, and it's very simulation dependent, but you could find something that way.
And also the EFT approach, of course, you can't look for resonances and stuff that way.
Why not?
Well, I mean, because the EFT is you're usually below the scale of the new physics, right?
Oh, so it's more of a tails.
In some sense, well, it's it's the low end tail. I mean, that's what EFTs do, right? You integrate out heavy stuff, and then you.
But you would see a deviation from standard model.
Yeah, it's like contact interactions, basically. That's what it is, right? And then you have to be careful with form factors, and so.
Yeah.
It's not trivial, also. Okay, I have to go home too.